Welcome everybody to today's session on electric motor and NVH. This is the second part of this week's Lunch and Learn series on electric power testing. My name is Dodo Husman. I am your host for today, and I have invited Mitch Marks, our Business Development Manager for electric power testing. Hi, Mitch.
Hello.
If you have any questions throughout the presentation, you can get in contact with us through the Q&A field. We will record the session and send the recording together with the slides to all of you. I am now going to hand over the word to our speaker and wish everybody a lot of fun.
All right. Thank you, everybody, for coming again. As Dodo mentioned, this is part two of a two-part series on electric motor noise and vibration. Last time we went over an introduction to noise and vibration electric machines, some of the sources, some of the why we cares, and some of the testing involved with that. Today, we're going to go through a case study and some light analysis. 15 minutes is not much to go through analysis on an infinitely complex topic, but we really hope we start the brainstorming process. So with that, I'll jump into it. Once I get PowerPoint to work. There we go. Agenda. First of all, we're going to introduce what we went over last time, just a brief recap. We're going to look at the measurement of noise and vibration and electrical signals. In a case study, we're going to go through some efficiency mapping with vibration, kind of a traditional powertrain test, but with the inclusion of vibration. And then we're going to go through some NVH ramps, including efficiency, so the other side of the coin. So, introduction of vibration in electric machines. As we went over last time, the electric powertrain is really this beautiful multi-physics problem where we have a battery outputting a DC current, an inverter that's turning on and off switches at a tens of kilohertz rate, create this pulse width modulated voltage signal, which results in a current signal that's got some harmonics. My poor art skills, as we're all used to by now. This AC electrical signal is feeding an electric machine that's translating that electric signal into magnetics into rotation. But what we get is when we have those pulses of voltage and current, we're getting pulses of magnetic, we're getting pulses of torque, and there's some filtering with the inertia, there's some electrical filtering, but at the end, in that mechanical output, we're going to have some torsional vibration just due to those switching effects of this multi-physics problem. So the thesis and what I want to get to at the end of this presentation is that there is a value to look at the inverter, the electric machine, as well as the mechanical output, including noise, vibration. Why measure both of these signals? Why include electrical and mechanical noise and vibration signals in the same data set? I get to live in the idealized world a little bit, but in the idealized world, we could have a single test to do both noise, vibration, and powertrain. It could be a single test stand or a single test format, single piece of data equipment, with really the goal of reducing capital costs. The more we can condense and simplify, the more budget we can have for other things. But what I actually think is the most important, and understanding that most groups do have separate departments, they might already have all this capital equipment, is by measuring both electric and noise and vibration, we really start to increase communication between groups. Noise and vibration changes are going to affect efficiency. Efficiency changes are going to affect noise and vibration. And there's this little world of calibration that has to deal with both of them. The more of these signals we can bring into one place, the more communication we can have, the more common vocabulary we can have, and the faster development we can have. Time to market is kind of king right now. Experience is a big part of this. Efficiency is a big part of this. So all these worlds come together, and faster development is going to result in better products, better time to market. We have this new fun world of sound design coming up where people are actually looking at designing electric machines and power electronics to make fun sounds that give a vehicle soul. And that is absolutely going to be inclusive of voltage and current and then vibrations. And then we get into things like fatigue characterization, failure testing, source path contribution, all these traditional factors. And as same as last time, I have my little graphic up here of voltage and current ramping up. So we're loading a machine. This is actually an aerospace test with a load cell measuring thrust. We can see load going up, voltage current going up, and then our vibration going up. We have this nice picture connecting all the signals. So my case study. I had some partners at a university, Illinois Institute of Technology. They do really great work there. That let us do some tests for noise and vibration in an electric machine. It's a three-phase traction motor. It's a little unique in that it's a PM machine with a wound field excitation, so it actually has a variable field current for variable magnetization. The test runs, as I mentioned earlier, we're going to do point-by-point efficiency map, a really basic map, and then some ramps at different loadings. And then what are we measuring? Well, we're measuring inverter voltage and current, torque and speed, vibration, and noise. And this, what I have in front of you, is one of my favorite gadgets that we sell here at HBK. This is an acoustic camera. So basically, it's a camera with 36 microphones in a very particular array, and we record a video, and we plot this little frequencies plot here, and we see this blue line. This is what we select to display on the video to highlight what the noise source is. So we can see here that we have this noise source that is at this frequency, and we can see this little triangle here to identify where our noise is coming from. Really fun gadget, and we get a nice view of the electric machine, kind of our test setup, and this noise and vibration factor. So the test setup we used, and here's my product pitch for the day. We had the device under test. We were measuring three-phase currents, accelerometers, and we were bringing those into one common data acquisition system, which is our Genesis eDrive. We were doing real-time display and plotting and measurement with our perception software. So we had this real-time feedback of voltage, current, frequency signals. But since we do store all data and we record all data synchronously, we're able to then export that data to BK Connect and do some of the more in-depth post-process analysis. So it's a really really smooth format for doing some cool analysis and doing so very quickly with a small set of equipment. One measurement equipment, different sensors obviously, and then the visualization software and the really hardcore post-process software. So test one, efficiency mapping with vibration. So to keep it simple, I did a 12-point efficiency map with a fixed field current because we started getting into a lot of mapping with the different field currents. And I'll just walk you through what we have here. As you all probably know, efficiency map is set a torque, set a speed, take an efficiency measurement. Increase your speed for a given torque, take efficiency. Increase your speed, take efficiency. And we went through a map like this. We took short triggered segments of measurement. So each one of these segments, I believe, is half a second. So I throw a trigger here. I take a measurement of voltage and current. I've got voltages in blue, my currents in red. I apologize for these being a little hard to see, but I also do this for my torque speeds and efficiencies. So I take a 1 second measurement of torque, a 1 second measurement of speed, a 1 second measurement of efficiency. And then I've also done vibrations. And rather than do the real-time vibrations, the raw signal, I decided to take an RMS of vibration just so I could have a trace that had some meaning to me. So I have two accelerometers. I have accelerometer 1 and accelerometer 2, where I'm measuring my RMS vibration. And this is just a really nice way to have all these signals displayed in one place. And what we find is that, for a given speed torque combination, so I think this was 1,000 RPM, this was 2,000 RPM, and this was 3,000 RPM, 1K, 2K, 3K, with varying torques. So my torque is going up. We see that we have this really kind of strong presence of vibration at 2K RPM for this given field current. And what this might tell us is, instantaneously, as we're going through these efficiency maps, as we're making our engineering changes, this might be a point that we want to avoid because my noise and vibration person said, Mitch, you should really avoid vibrations over a certain threshold. So I think this is really interesting that you can get that instantaneous feedback and identify places where there might be resonances due to your changes. And we can really start to monitor how controls affect vibration, how changes affect vibration. Now, naturally, I need to take this a step further and make this a graph that actually made sense because my little point-by-point graph is not the easiest to look at. So I took all those efficiency points and I plotted a heat map with speed on my X and then torque on my Y. And again, this was only 12 points, but for example's sake, I think it does a really nice job. And I plotted that efficiency map. And we can see we have this really high efficiency area, high torque, high speed. And we have this upward trend of efficiency with loading. And then I also plotted this map for the same 12 points for my vibration. And for me, as a guy with a motor background, I have some intuition looking at these maps as to what I'm looking for. And right here, I can see that I've got this really high vibration area. And if I'm given thresholds, if I'm given intuition for how I want to operate my machine, this might tell me that this is going to cause issues downstream. This is going to have issues with the gearbox. This is going to have issues somewhere. So I think this is a really quick and dirty way with just a couple additional measurements to have a quick understanding of the vibration state. And just like I pointed out last time, we can see that this particular high efficiency area has a pretty high vibration. Maybe we want to avoid this point. But again, my main point here is that we can do these really quick checks on how our changes are affecting other groups and use the same tools that we might already be used to. And again, increase that communication, increase that delivery time, reduce the back and forth between groups. My next example is doing ramps tests. So ramp test is really, we fix a torque. So torque equals X, and then we ramp speed from 0 to speed back down to 0. And this really gives us a nice frequency spectrum versus speed for what our noise and vibration signals are. Now, again, as the motor guy, there's certain things I want to look at. And I measured voltage and current, but I actually translated them to my control variables. So in this plot, I have IQ in blue and ID in red. And I'm really looking at those control variables during this sweep, this speed sweep for a fixed torque. As I mentioned previously, I have this I field. I have this field current value. This is really telling me the rotor state of magnetization. But for me, that's a state variable. I want to record this. I then ramp my speed in green. I've got my fixed torque in pink, and I can see my efficiency that's changing dynamically on me. And this is really important because this is one of the cool things we can do with our HPM equipment. I then have my accelerometers and my microphone. So I'm measuring all of these in one place. I've got this one common measurement tool and one common visualization tool. But as the noise and vibration engineer, having these electrical signals here, one gives me the ability to do post-process analysis on these, as we'll look at in a moment, and really understand that source path contribution of my accelerations and my microphones. But also for communication purposes, if I make an NV change and something is really bad with the efficiency, I can immediately, one, identify my efficiency and know if I've drastically changed that. But two, if I get a change from the powertrain group and I run it and I identify a noise or vibration issue, I can say, guys, I ran point X and your field current was this, your ID and your IQ were that. Here's my torque and speed. Here's the exact state that this test was in. I need you to fix this. This is a big problem for me. But again, one graphic location, one common vocabulary set, one data set, and you know the state of your vibration, the state of your torque, the state of your speed, voltage, current. Now, for analysis, we did some spectral plots on this. Again, the spectral plot is we're putting frequency on the X. This is like FFT frequency. And then in this example, I have what looks like order on the Y. So we're looking at this, and we run our spectral graph, which is showing this frequency versus speed. So these bands here, these are increased frequency presence with increased speed for voltage, current, acceleration, and microphone. And what I found, being again the motor guy, is that when we start doing acoustic analysis, because this is really looking at acoustics, this is the inverter switching at 10 kilohertz. Voltage gives us a really fantastic signal for translating to acceleration or microphone, because it doesn't have that filtering, it doesn't have that noise source that's getting caused through the sensor. It's just this really pure signal that we can really start to look at acceleration. But we get the full source path. We get the contribution of voltage to current, and we can see how much is filtered out of that harmonic signal going from voltage to current. We can see how much is filtered between going from current to acceleration or going from voltage to acceleration, whichever you're particularly interested in. And then we can see how that correlates with microphone as well. And we can get this full picture of having all these things in one place. And when we were running this test, one really interesting thing we found was that we would assume that current and voltage have this direct correlation with acceleration. What I mean by that is our bands in voltage and our bands in current, our brighter bands result in stronger frequencies, would result in the same order bands in acceleration and microphone. What we actually found for this particular machine is that the stronger current and voltage bands correlated with weaker acceleration bands, and then the weaker acceleration bands correlated with stronger, or excuse me, the weaker current bands correlated with stronger acceleration bands. So we didn't exactly know why this was. This did merit further analysis, which we might have in a follow-up at some point. But just really interesting stuff, and you can't just make these assumptions that one's correlated to the other. At some level, there's a transfer function between current and acceleration, or between voltage and acceleration. So understanding these things is powerful, and having all this data in one place during these tests gives us a way to identify where these problems are coming from, identify possible solutions for that. And then lastly, again, because I'm a motor guy, I like my little maps here. So I wanted to see, because we can measure that efficiency dynamically in our measurement equipment, we use some special tools where as torque and speed are increasing, we can measure efficiency very accurately in dynamics. So I wanted to take those measurements from my 2 ramps tests. So I believe this was from, or excuse me, my 2 different loadings for my ramps test. So this was at 13 Newton meters, and this was at 26 Newton meters. And I just wanted to plot an efficiency map to see what I got. And I don't have the best data sets because I only have the 2 torques. But what I did was I plotted my efficiencies in the contour versus speed on the X and torque on the Y. And we can see that we get that same upward trend, that same high efficiency in the right-hand, upper right-hand corner. For the higher loading, we get that same trend. And we can really correlate pretty nicely with what we have going on here. And again, we can use these tools to say, okay, I've made X and Y changes to noise and vibration, and I can see this relative change in efficiency from one state to another. And is that acceptable or is it not? Or we can take these traditional efficiency maps. We can really start to understand how our changes affect efficiency and look at them in ways that efficiency engineers or powertrain people might want to understand them. And again, we get that really strong correlation because we use that cycle detect feature. To do this, it does require a high dynamic power analyzer and a high bandwidth torque sensor. But again, increase communication, reduce capital if possible. So with that, I'd like to thank you guys for attending today. As always, please feel free to reach out in the chat or to me directly. You can scan these codes with your phone and we'll be happy to get back to you. I will note, if you're interested in the noise and vibration topic, we will have a webinar in mid-June being hosted by one of our noise and vibration experts, speaking to it more from the noise and vibration side than from the electric motor side. And also, before Dodo yells at me, I'd like to shout out our LinkedIn group, our electric power testing group that is on LinkedIn. You can get to that through our webpage or directly searching through LinkedIn. So Dodo, back to you.
Thank you, Mitch, for another great presentation. It always amazes me how you do this within 15 minutes. Tomorrow we'll host the last part of the series on transient power testing. It's a follow-up on the first session that we hosted 3 weeks ago. So I hope to see you all there. Thank you, Mitch. Thank you, everybody, for participating. If you have any questions, feel free to ask them in the Q&A field now or email us directly. Thank you, everybody.
Thank you, everyone.